I am B. Janardhan Reddy. In this video, I am going to explain Ohm's law and its limitations. Do all materials obey Ohm's law? Is the ratio of V and I in case of LED constant? And what are ohmic and non-ohmic materials? All these things we are going to see in this video. Let us remind Ohm's law once again. See here, the potential difference, that is V, between the ends of a conductor is directly proportional to the electric current I passing through it at a constant temperature. And we can write this mathematically as V is directly proportional to I. That is, when I is more, V is more. When I is less, V is less. Okay, so V by I. So the ratio of voltage and current is constant at constant temperature. When temperature is constant, V by I is constant for a particular conductor. And this constant is called as the resistance of the conductor. It is denoted by R. So V by I equal to R. Now the question is, do all materials obey Ohm's law? Does LED, that is light emitting diode, obey Ohm's law? That we are going to check by doing an activity here. Here I am making a circuit connecting LED. See here, this is a dry cell of 1.5 volts. It has two terminals, positive and negative terminals, and here is an ammeter. It measures the current in a circuit in milliamperes. And this ammeter also has two terminals, negative and positive. The black knob shows negative terminal and the red knob shows positive terminal. I am connecting negative terminal of the dry cell to the negative terminal of the ammeter, and I will connect the positive terminal of the dry cell to a resistor, and the second end of the resistor I am going to connect to the positive terminal of the LED, and the negative terminal of the LED is connected to the positive terminal of the ammeter through a key. See here, an LED has two leads or terminals. Okay, so the longer side is positive terminal or anode. It is also called as anode. The smaller side is negative terminal and it is also called as cathode. So across the two terminals, I am going to connect a voltmeter to measure the voltage between the two terminals. Okay, so this is a circuit diagram for LED. Now I will close the switch here. Then what happens? You see here, so no current is flowing in the circuit. That means LED does not conduct current to pass through it. LED does not conduct. It's not allowing current to pass through it. Even though some voltage is there between the ends of the terminals. Okay, so between the terminals some voltage is there. How much voltage is there? 0. Some 4 volts voltage has been applied between the two terminals, that is anode and cathode. Even though that some voltage has been applied between the two terminals of the LED, it is not conducting, it's not glowing. So the LED is in half position only. Okay, so ammeter shows no current, that is in the circuit no current is flowing actually, and because of this voltage some voltage has been developed between the two ends or two terminals of the LED. So see here, V equal to 0.4 volts, I equal to 0 amperes or 0 milliamperes. Okay, so I have connected here one resistor, because if more current is allowed to pass through LED, it will get damaged. In order to control, in order to limit the current in the circuit, I have used this resistor. Okay, so when 0.4 volts voltage has been applied between the two terminals of the LED, the current passing through it is 0 amperes or 0 milliamperes. Okay, so let us note down these values in the table. Serial number 1, potential difference V equal to 0.4 volt, that is potential difference across the two terminals of the LED, and current flowing in it is 0 milliamperes. Okay, now I am increasing the voltage by connecting two dry cells in series. Here negative terminal, I am connecting to the negative terminal of the ammeter. Positive terminal will be connected to the resistor. Now if the switch is closed, the key is closed, what happens? You see here, now LED is conducting, that means it is allowing some current to pass through it, so it is glowing dim. So what is the voltage between the two terminals of the LED here? It is 0.8 volts, and current passing through LED is 4 milliamperes. So let us note down these values. V equal to 0.8 volts, I equal to 4 milliamperes, means 0.004 amperes. So let us record these values in our table. Serial number 2, 0.8 volts, 4 milliamperes. Okay. Now I will further increase the voltage between the two terminals of the LED. See here, here I am using 3 dry cells connected in series. Okay, let us complete the circuit. Now close the key here. Now LED is glowing more. It is on and current is passing through LED. So what is the voltage between the two terminals of the LED here? It is 1.2 volts. And how much current is passing through LED? it is 10 milliamperes. So let us note down these values here. V equal to 1.2 volts. Okay, that is the potential difference between the two terminals of the LED is 1.2 volts, and when 1.2 volts potential difference is applied, isn't it, how much current is flowing through it? It is 10 milliamperes. Okay, otherwise 0.01 amperes. Okay, so let us note down these values in the table here. Serial number 3, 1.2 volts, 10 milliamperes. Okay, I will further increase the voltage, that is potential difference between the two terminals, anode and cathode, of the LED. Here I am using 4 dry cells connected in series. Okay, so let us complete the circuit. Here I am connecting, and the positive end is connected here. Now let us close the key. Now see here, in this case more current is flowing through LED. You might have observed the color of LED is changing depending upon the amount of current passing through it. Okay, so now the voltage between the two terminals of the LED is 1.6 volts, and how much current it is allowing through it? It is 20 milliamperes. Let us note down these values. So voltage V equal to 1.6 volts, I equal 20 milliamperes, that is 0.02 amperes. Let us note down these values in the table. 1.6 volts, 20 milliamperes. Okay, I am increasing the voltage again. See here, 5 dry cells have been connected in series. Let us complete the circuit by connecting negative terminal to the negative terminal of the ammeter here, and positive terminal will be connected to the resistor. Okay, now let us on the key here. See here, so in this case LED is glowing brightly. Okay, that means more current is flowing through it. Let us note down the voltage and current. Voltage applied between the two terminals of the LED is 2 volts. How much current is passing through it now? It is 50 milliamperes current is passing through it. Okay, so V equal to 2 volts, I equal to 50 milliamperes, that is 0.05 amperes. I am noting down these values in the table here. Serial number 5, potential difference is 2 volts, current is 50 milliamperes. Okay, now I am calculating V by I value in each case. See here, V equal to 0.4 divided by 0 means infinity. That means LED is offering infinite resistance when 0.4 volts potential difference is applied between its terminals. Okay, that means no current is passing through LED. Now the second case, you see here, when 0.8 volts potential difference is applied, 4 milliamperes current is flowing through it. 0.8 divided by 0.04 equal to 200 ohms. 1.2 like this. Here I am calculating V by I value in each case. Now you can observe one thing. Here V by I value is not constant, isn't it? So when the voltage is gradually increasing, isn't it? What happens here? Current also increasing, but the V by I value, the ratio of V and I value is not constant. So V by I value is not constant means it's not obeying Ohm's law. So LED doesn't obey Ohm's law, isn't it? So the resistance of LED is changing depending upon the potential difference applied between its terminals. Okay. So let us draw the VI graph, voltage versus current graph of LED, taking voltage on the x-axis, current on the y-axis. Here I am drawing the VI graph. What type of graph we get? Let us see here. This is a graph paper. So these are the values just now we got in case of LED, x-axis, y-axis. Here on the x-axis I am taking voltage in volts, and on the y-axis I am taking I, that is current in milliamperes. So 0, 0.4 from here to here, 0.8, 1.2, 1.6, 2.0, 2.4. Okay. Next 10 milliamperes, 20, 30, 40, 50 and 60. Okay, so here I am showing the scale here. On the x-axis 1 centimeter, that is from here to here, 1 centimeter length I have taken as 0.4 volts, otherwise 1 millimeter, isn't it? 0.04 volts. And on the y-axis, the scale is 1 centimeter equal to 10 milliamperes. That means 1 millimeter equal to 1 milliampere. Okay, so for 0.4 volts, how much current is flowing through the LED? It is 0 only. Okay, here one point I have shown. Next, for 0.8 volts, the current passing through LED is 4 milliamperes. See here, here. Next, for 1.2 volts, 10 milliamperes here. And for 1.6 volts, 20 milliamperes here. And when the potential difference between the anode and cathode is 2 volts, then how much current is passing through LED? It is 50 milliamperes. Say here. Okay, so let us connect all these points. We will get a graph like this. So here it is non-linear. We got a non-linear graph. It's a curved graph. The graph is a curve, not a straight line passing through the origin in case of what is that conductors. So LED doesn't obey Ohm's law, isn't it? And VI graph of a conductor, again I am showing in the lab activity of Ohm's law. I showed this again. Here I am showing. See here. These are the values we got in lab activity of Ohm's law that I explained in my previous video. Okay. See here. So x-axis 1 centimeter equal to 1 volt, that is 1 millimeter equal to 0.1 volts. Y-axis 1 centimeter 0.5 amperes, 1 millimeter equal to 0.05 amperes. So these are the values. Okay, so for 1.5 volts, it is 0.4 amperes. Okay, next 3.0 volts means 0.8 amperes, 4.5 1.2 here, 6.0 1.6 here, 7.5 2 amperes. Now connect all these points, we get a straight line passing through origin. Okay, so this is in case of the materials which obey Ohm's law. Okay, so in case of materials which obey Ohm's law, the VI graph is linear. And we have seen in the earlier one, the VI graph for LED is non-linear. That is, we got a curved graph. Now I am explaining the limitations of Ohm's law. See here, Ohm's law is valid for metal conductors provided the temperature and other physical conditions remain constant. Isn't it? So the resistance of a conductor is temperature dependent. Isn't it? If temperature changes, the resistance also changes. At that time, Ohm's law will not be valid. So Ohm's law is valid for conductors, that is metal conductors, when the temperature is kept constant and the resistance of the material changes with temperature. For changing temperature, the VI graph for a conductor will be non-linear. We won't get a straight line when temperature is changing. That means Ohm's law does not valid for metal conductors when the temperature is not constant. Okay. And Ohm's law is not applicable to gaseous conductors, that is through discharge tubes. When current is passing through discharge tube, Ohm's law is not valid. Okay. Ohm's law is not applicable to semiconductors such as germanium and silicon. Okay. Classification of materials based on Ohm's law, that is whether materials obey Ohm's law or not. Depending upon that, we can classify the materials into two categories. So let us see what are they. Based on Ohm's law, materials are classified into two categories. The first one is ohmic materials and the second one is non-ohmic materials. Now, what are ohmic materials? The materials which obey Ohm's law are called ohmic materials. The example for the ohmic materials is metals. So metals are ohmic materials. That means the VI graph for metals is linear. We get a straight line passing through the origin. See here, the VI graph for the ohmic materials will be linear like this. Okay. Then what are non-ohmic materials? Let us see here. Non-ohmic materials means materials which do not obey the Ohm's law. So the materials which do not obey Ohm's law are called non-ohmic materials. Examples: semiconductors such as germanium, silicon, LED, that is light emitting diode, and gaseous conductors. These are the non-ohmic materials because they do not obey the Ohm's law. The VI graph is non-linear for these non-ohmic materials. The VI graph for the non-ohmic materials will be non-linear. Just now we have seen the VI graph of LED. The same again I am showing. So here the VI graph is not a straight line. It is non-linear graph we get. Okay, so this is all about the non-ohmic materials, ohmic materials, and limitations of the Ohm's law. Thank you.